I'm Frances Westall. I'm a geologist. I'm Director of Research at the CNES in Orléans. I've been there for 14 years now, and I'm head of the research group, the EXOBIOLOGY research group there. We do quite a lot of different things, from prebiotic chemistry to fossilizing microorganisms to studying the environment of the early Earth, the sedimentological environment of the early Earth, to studying traces of life on the early Earth, and we're very much implicated in the European-Russian mission EXOMARS to Mars. So, missions to Mars to search for life. So what I'm going to talk to you today about is, in fact, I've got quite a few different, can we see that? Yes, just about, I can't. We have quite a, there are a number of different topics I'd like to talk to you about. It's not just about early life, but it's about the setting of early life as well, the habitat of early life. So I'm not sure, how many of you are geologists? Please raise your hand. Okay. Biologists? Chemists? Physicists? Something else? Okay. So what I want to talk about today is, first of all, place early life in the geological time scale, talk about the habitats of early life, the sedimentological and the hydrothermal habitats. Because I'm going to be talking about the fossilized traces of life, I think it's worthwhile to have a look at what characteristics of microbes can be fossilized, what can be preserved in rocks. Then briefly look about how these traces can be preserved, fossilization, biosignatures. Then we'll have a look at what is in the rock record, traces of early life. And I've divided it into the two main groups of prokaryotes, the phototrophs, those using light energy for for energy, and chemotrophs. Sorry, there'll be some spelling mistakes. I spent 14 years in France and it's done nothing for my English spelling, so I'm now mixing English and French spelling, so just bear with me, please. And the chemotrophs that use organic matter, carbon, and inorganic sources for energy. And then, if we have time, I want to talk a little bit about extraterrestrial life. Now, Hervé has spoke about that yesterday afternoon. I'll speak, if we have time, I'll speak about it from a different point of view, and specifically from the point of view of the European-Russian mission EXOMARS, which wasn't addressed yesterday. So let's go on to the first part, which is early life in the geological time scale. But first of all, okay, what is, why have I got this here? Sorry. I've been doing some things to my presentation this morning, not feeling quite good, but anyway, so we'll just have a look. First of all, if we want life, we need a habitable environment. So a very simple definition of habitability is an environment where you have the simultaneous presence of liquid water, carbon, other essential elements such as nitrogen, oxygen, phosphorus, sulfur. Those are the main life essential elements, as well as the transition metals, and these are going to be important, and energy from chemical, heat, or light sources. Now, I'm talking about life as we know it. I'm not talking about life based on silicon or something else. I'm just limiting myself to life as we know it. We've had talks this week on the early environment of the Earth, so from Hervé, so I don't think I need to, Hervé and Francis Albarade, so I don't really need to go into this at all. Two things I'd like to mention. Again, what I'm going to tell you about is from my point of view, which may be different to other people's, and is also debatable because it's a personal point of view. So I think the important thing is that when we could have had liquid water at a reasonable temperature on the surface of Earth, so that organic molecules can get together, assemble, and somehow or other form of the first cells. And this appears to be in the period 4.4 to 4.3 billion years ago. So that's an important date. And then there's also this phenomenon which is quite debated now, the late heavy bombardment. Was there perturbation of in the asteroid belt by movements of Jupiter and Saturn that caused asteroids to come into the, get out of orbit and to come into the inner solar system and start bombarding the inner planets? It's still an hypothesis based on dating of lunar rocks, but apparently there's some question as to whether the lunar rocks dated are really non-impact rocks, what we call mare rocks, those formed by the sort of non-impact rocks, or really the older crust. So there's a question here: if there was a period of bombardment, how would that have affected life on Earth if life had appeared earlier? And I think life certainly could have appeared in this period of time. How could that have affected life? Would life have been extinguished completely? Would it have evaporated all the oceans? Would it have evaporated only something like 400 meters of the oceans, as some people think? Or would there not have been sterilization at all? In fact, the models say, always state between something like 0 and 6 planet sterilizing impacts. I mean, that's 0 is 0. So I think there's a big question mark there, and certainly there seems to be no particular evidence on the Earth that this happened. Still quite a lot of bombardment from meteorites and so on, but not necessarily planet sterilizing bombardments. A thing to keep in mind, it's not particularly important for the Earth, but it is very important for a planet like Mars, for instance, or other planets. When we talk about habitability, we're actually talking about habitability from the microbial scale, which is quite different to habitability at the planetary scale. A whole planet may not be habitable, but a planet may have habitable zones. So we'll come into that when we look at Mars. And just a last thing, it's got nothing to do really with the talk, but in terms of habitability, for long-term habitability, you need some kind of recycling of the crust, because organisms living at the surface of the crust over billions of years are going to exhaust the nutrients at the surface. So you need overturn of the surface to bring them back up. And this is through plate tectonics. So, but that's sort of for further evolution. Anyway, now I like to start with I like setting the scene. When we look at the Earth from space today, we see something like this. It's an absolutely magnificent view, beautiful blue ball, marble, with some continents on it. And I'm sorry, I'm very subjective. I've centered it on South Africa because I was born in Johannesburg. So this is one of my favorite places on Earth. But that's what we see today. If we went back 4 billion years, that's what we would see. Something with no or extremely very few lands exposed emerge from the surface of the ocean. The Earth was, we could define the early Earth basically as an ocean planet. Hervé will have spoken to you about continental formation, I think. The continents were mostly submerged. We're looking at a planet that really was almost completely covered with water, with just the volcano tops and certain other areas emerged. So when we want to study the early Earth, as Hervé will have told you, we have a huge problem, and that is the lack of rock record. The rock record is these are our history books, but we don't have them. This map shows the distribution of what we call Archean rocks older, between 4 billion years and 2.5 billion years old. They're not very many, and most of them are highly metamorphosed, highly altered. With the stars, we have rocks that are about 3.5 billion years old, And the two areas where we have well-preserved sedimentary rocks are in South Africa, in the Barberton Greenstone Belt, east of Pretoria, and in the Pilbara Craton in the northwest of Australia. And the reason why I mention well-preserved sedimentary rocks is if we want to look for traces of life, life needs water. The best place to look for traces of life are in rocks that formed in water. So this is why it's important. And we want well-preserved rocks because highly altered rocks, maybe they had signatures. For instance, the Itzhak province here in Greenland, Isua, has sedimentary rocks, but they're highly altered, highly metamorphosed. There have been studies that have looked at the carbon isotope signatures in these rocks and have decided, based on these isotope signatures, it's been claimed that these rocks hosted life. Frankly, I think it's quite probable that these rocks that life was there at that particular time. But the same carbon isotope signatures can be found in abartic carbon in meteorites. So, but I think that's sort of splitting hairs in a way. But the best preserved, the oldest best preserved sediments are only found in these two regions. It's not a very large sampling area. Okay, now let's get on to life in the geological time scale. As I mentioned, I think life, given the ingredients that we have, life could have appeared as soon as the general average temperatures of the oceans were sort of low enough, let's say about 80 degrees, to permit the assemblage and combination of the important molecules that created life. 3.8 is the Isua date, where there are isotopic signatures of life. And I think the most ancient traces of life, well-preserved traces of life, date from this period, 3.5 to 3.3, 3.2 billion years. So I'm going to concentrate here, and these traces will be traces of very simple life forms, prokaryotes. We're not far off the origin of life, so we're still at the simple prokaryote stage. But you will see, in fact, that although the traces of life that I'm going to show you represent prokaryote, we think prokaryote, or the organisms, microorganisms that are similar to modern-day prokaryotes, there's quite a diversity already in these rocks. So, oh yes, but the problem is, as I mentioned, we've lost, because we don't have any well-preserved rocks older than 3.5 billion years, we've lost the old record of life. We've lost nearly 1 billion years of the history of life on Earth, and that's serious, which is why I hope some of you are going to carry on and search for life on Mars for me, because unfortunately one has to start young. And just a little anecdote, at the end of the 1990s I worked at the Johnson Space Center as a geologist, and when I went there I thought to myself, I'm going to be the first geologist to go to Mars to search for traces of life. Well, I'm still here, and time is passing by, and we may be sending geologists to Mars in 2014, which will be a little bit late for me. So anyway, hang in there, youngsters. Anyway, so I want to talk now about the habitats, about the sedimentology, to paint the scene for you. As I mentioned, we only have these rocks to base our information on, but I have to say these rocks are so beautifully preserved. Hervé has been to these areas as well. He can confirm they are exquisitely preserved for a specific reason, which I'll come to in a while. from these rocks, I want to talk a little, give you a little idea about the general environment, environmental conditions 3.5 billion years ago. But first of all, just we'll compare them to conditions to today. Anyway, so what we can read from the rocks, we can read from the rocks that the average temperature, and there is some debate about the temperature of these that's represented. What I want to, I've put an average temperature of about 50 degrees. There's some estimates 70, 80 degrees, other estimates 30 degrees. And I'm putting 50 degrees for the specific reason that the environments that I'm going to show to you are so strongly influenced by hydrothermal fluids that they that in fact at the sort of at the sediment or rock water interface where these organisms lived, these are the temperatures that about the temperatures that they will have been experiencing, possibly even higher. So compared to today, the water was a lot hotter. The pH of the water, in fact, was more slightly more acidic than today. The reason being that the major component of the atmosphere was carbon dioxide. Carbon dioxide dissolved in water makes a weak acid, so we have slightly acidic ocean waters compared to the neutral waters of today. There was also always a tiny amount of oxygen in the atmosphere produced by abiotic processes. These processes include photolysis of water vapor in the upper atmosphere, radiolysis of water at the surface of the ocean because there was no ozone layer, so very high radiation rate. Also, because of the amount of hydrothermal activity going on, there's the pressurized hydrothermal fluids coming up to the surface were boiling. So when water boils, you can get dissociation of hydrogen and oxygen. So there's always a small amount, but very small amount of oxygen around compared to today. Radiation, I mentioned, no ozone layer, no oxygen, no ozone layer. So quite a high rate of radiation. This is a value based on work by Charles Coquelle and his student Raven, published I think in 2004. In fact, this is the weighted radiation value with respect to the effects on DNA. So if today the flux of UV radiation to the surface of the Earth is about 1 watt per square meter, 3.5 billion years ago it was about 54 watts per square meter, going up to maybe 1,000 in the worst case scenario. So huge radiation rate. Still, we're looking at a very volcanic planet with a lot of hydrothermal activity and still quite a high impact rate from meteorites. And we see layers of spherulites produced by impacts in these ancient sediments as well. So we can say that the environment of the early Earth was extreme in comparison to the environment of early day. However, this environment is more normal for any other planet that we come across than the environment that we find on the Earth today. So change your mindset. Our Earth today is extreme and we are the extremophiles. So I'm going to show you some examples of the habitats. I'll use one example, the Barberton Greenstone Belt here, east of Pretoria and just on the border of Swaziland. It's a beautiful area. The geology, for the geologists of you, the Greenstone Belt is folded. This is the Onverwacht Belt. It consists of mostly volcanics and interlain by thin layers of volcanic sediments and intruded by granitic granitic plutons. So this is the Swaziland border and the study area is in this area here. Where I'm going to show you photographs from the field. You'll see rocks, outcrops of rocks in the field. But when you see these outcrops of rocks, keep in your mind how they formed. I'm going to show you sediments that formed in sort of the shallow water basins. Here, for instance, the light grey represents the volcanic rocks, the pillow lavas, the mafic, ultramafic lavas, and the dark grey stippled areas represent the sediments that are derived from these lavas. The lavas eroded, the sediments were deposited, and they were deposited very close to the source, and there was always volcanic activity around, volcanic dust, volcanic ashes being blown into the atmosphere and depositing as well, also river water with rivers coming in. And note the importance of these hydrothermal veining. I'll show you, it was all pervasive. So hydrothermal vents and infiltrations of the sediments everywhere, under the water, also on the beach. For the non-geologists, I'm going to show you some photographs of modern environments just to give you an analogy, because for we geologists, we can look at a rock outcrop and we see it already in 3 dimensions. But for the non-geologists, it's quite difficult to put the 2-dimensional image into 3 dimensions. So just imagine a mud flats. This is the Bay of Mont Saint-Michel, intertidal zone, mud flats with tidal channels. Notice also, and this will come in a bit later, you can see the green colouring on the surface. Well, that green colouring is formed by mats of phototrophic organisms. They can, in between tides, they can reappear and they can form a mat on the surface. And we will actually see these kinds of mats formed 3.5 billion years ago. Here is a close-up. You can see the ripple surfaces, the ripple marks. Now we will see these ripple marks in 2 dimensions, in sort of cross-section in 3.5 billion year old rocks. If you cut through these sediments with a spade, this is the kind of structure you see. You can see the different layers of sediments, the grey, the black, and you can see them sort of crossing over each other. This sort of crossing structure is representative of the ripples. So when we see this in a rock, we know that it means ripples. It means wave action. So try to keep in mind a sort of 3D image when you see a 2D cross-section, if you can. Another thing that's important to keep in mind is that when I talk about about sediments 3.5 billion years ago, I'm talking about volcanic sediments. I'm not talking about stretches of white quartz sand or stretches of sort of cream-coloured carbonate sand from shells, ground-up shells. They didn't exist at that period. I'm talking about black sand, black volcanic rocks ground up. So this would have been the situation 3.5 years ago. So here are some photographs of the study area. You can see these beautiful, beautiful mountains. It's absolutely wonderful. It's a wilderness. It's just, well, Ava's got a big smile on his face. He remembers, yes. It's just fantastic to be able to go out into the wild and study the rocks. You see the grass is quite high. That makes looking at rocks also difficult, and it also makes it difficult to see the rocks when you walk over them. In fact, my husband, accompanying me a number of years ago on a field expedition, broke his leg because there was a boulder that he didn't see under the grass, and it went crack. Not a nice sound. This is one of the areas, the hillsides. This is, in fact, a typical view of how the rocks are exposed. There's a little road here, you can just for scale, a little cliff face here. Now these rocks were originally laid down flat, or more or less flat. Here, they've been lithified and they're vertical. They've been turned up vertical. So this cliff face, if you look at the cliff face from the side, you're actually looking at the surface of the sediment. If you look at it from the top, you're looking at the layers of sediment, a cross-section of the sediment. And the exposure is not brilliant because it's quite covered. But we can get still a lot of information from study of these rocks. This is a closer up image of this cliff face. And talking about the dangers of doing field work, I actually slipped down this cliff face and I nearly lost my finger. At the local hospital, they were about to cut it off. Anyway, I still have my finger, and I will spare you the details, but I still have my finger. So it's beautiful, but one has to take certain precautions. Anyway, now just look at this. This is a photograph of a rock exposure on the hillside, and you can see the different layering. Now think about the layers that I showed you from the Mont Saint-Michel. You cut through the sediments. And what we're actually seeing here, you can see some parallel packets of parallel layers at the bottom and at the top, and in the middle you can see some layers that are wavy, rippled. So what we're actually looking here, these parallel layers, these are layers of ashes that are falling into the water. They're being sedimented, and they are very extensive. Some of these layers are only about 1 millimeter, 2 millimeters thick, but we can trace them over 2 kilometers. We can go from one outcrop to another, and we've measured the whole section. We can trace them. So we've got a very good idea of the aerial extent of the environment. So we're looking here at volcanic ashes that are falling into shallow water close to the coast, and then they're being reworked by the tidal currents. And in fact, in some regions of this horizon, we see what we call oscillation ripples. These are typical ripples of the intertidal zone. So we know that the tides are reworking this material. It's falling, it's being reworked, and then more ashes are falling. So this is the environment. And again, just for comparison, I've put in the photo from the modern sediments from Mont Saint-Michel. Now, these sort of ripple marks, traces of the current environment, we can see also in thin section. We make thin sections of the rocks about 30 microns thick, so that we can observe them with the optical microscope. We can see a lot of structure in these thin sections. You can see the ripples, the cross-bedding structure, which is typical for current reworking of sediments, even in thin sections. In fact, the thin sections are one of the most important tools for a geologist. Even if I'm looking for features that in the end are 1 micron in size, the fossilized cells, I still need to look at the outcrop. I still need to look at the context from the sedimentary structures. And in fact, for a geologist, the study of thin sections in an optical microscope is so important that we're designing an instrument to make thin sections on a planet like Mars in situ. It's never been done before. We consider it to be super important. Anyway, and another image, a sketch of what the environment was like. We have the volcanic lavas, the basalts, the pillow lavas that Hervé showed you, overlain by sediments that are issued from the degradation, from the alteration, the mechanical breakup of these volcanic layers. These sediments are altered in turn because they're laid down in water. So they are altered by chemical processes in the water. But just a huge amount I've really perhaps exaggerated a little bit with these hydrothermal veins coming up, but they really were very pervasive. And these sort of funny bumps that you see are supposed to represent reworking of the sediment also by storms. The storms produce dunes. So we see these dunes in the sediments as well. And then getting closer to the coast, we have the coastal areas, the intertidal areas. Again, there's always meteoritic infall still at this period. And the ashes coming from the volcano. Okay, I want to say a little bit about the chemical composition of the seawater. The early sea waters were supersaturated in silica, and there are a number of sources of silica at that time. Silica would have been in the river waters from alteration of the volcanic rocks exposed. Silica would have come from being brought up by the fluids from the hydrothermal systems, and they were very common. And silica would also have been produced by alteration of the volcanic sediments in water. There's a process that we call devitrification, by which the volcanic sediments are altered to phyllosilicates such as clays, and in the process silica is liberated into the pore water. So the area was supersaturated in silica. This is very important because it is the supersaturation in silica and the fact that everything was very rapidly silicified. Sediments were silicified, the organisms that lived in the sediments were silicified, the volcanic rocks were silicified. Everything was very rapidly silicified. And this also is the reason why we have such superb preservation. Given the age, it's very good. So if you grind up the rock, you can measure the amount of silica that's in the rock. So we take this rock, we know it was volcanic sediments, very heavily volcanic sediments. We grind it up and we find 96% silica. That's huge. You take this rock, which in fact is the same as this one, but it's even more silicified. It's more than 99% silica. These rocks are the hardest rocks in the world. And in fact, you need a good, strong man to break them up, and a very good sledgehammer. So if you're tempted to go into the field, make sure you've got a brawny guy with you. Anyway, so another influence of the hydrothermal activity is not just the silica, the fact that silica has pervaded everything. We also see it in the mineralogy. Okay, I've spoken about silica enrichment, silicification of the rocks. In fact, the altered volcanic sediments are all, when they're altered to clays, eventually are altered also to silica. They're replaced by silica. But we also see it in the mineralogy. There's a certain horizon in this exposure, which is where photosynthetic microbial mats have been replaced by siderite, and we think that's due to hydrothermal infiltration. But I'll show you some details of this. I think, well, just very briefly, this is what we call a generalized stratigraphic column. The sediments are deposited one layer on another, and they're lithified. And the deposit of sediments here, it ranges from area to area, but the maximum thickness is about 30 meters here. And this, we don't know exactly how much time 30 meters represents. We do know, we strongly feel that this little horizon here that's a couple of meters thick was probably deposited as volcanic ashes. We think it's probably deposited maybe in a period of 2 weeks to a month or so. But the other thicknesses, we don't know how long it took for these layers to be deposited, but that's all the information we have. So even within a thickness of 30 meters, you can have changes in environment. If we're looking at thousands of years, there are changes in the environment that occur during this period of time. So at the base, this is a typical geologist's way of presenting sediment lithology, or the composition of the sediment, grain size. The more to the right this line is, the coarser the grain size. So we have, so let's say you have the volcanics, the pillow lavas here, and deposited on them are sediments that have been influenced, that were deposited close to the shore, but not exactly on the shore. And they were influenced by storms, and they made big waves, dune-like deposits. And then there was a quieter period where we have very thin parallel bedded sediments that we think are siderite replaced photosynthetic mats. And then there was more agitation, more storm events, and finally volcanic activity. But what's important here is you can see these white streaks that are parallel to the sediment layers and also cross-cutting. These represent hydrothermal veins. The sediments were lithified, and the hydrothermal veins were coming through, cutting through them, spreading out parallel to the bedding planes. This was very strong in the lower part of the deposit, and there's this black layer, in fact, is almost purely hydrothermal silica. And in the column here, well, to the right, we have the geologist descriptions of the environment of deposition. We call them upper offshore to shore face. The beach area would be upper shore face, and so on. So that's just to describe the environment of deposition. And then there are two columns here that show the distribution of traces of life as we've found so far. This is published last year, so we're still working on this, and in actual fact, this is going to change due to what we found recently. But we see traces of phototrophic microbial mats, and I will show these images and what they look like later. We find these traces throughout the sediments. They were everywhere. Not necessarily well preserved, sometimes well preserved, sometimes not preserved. And the chemotrophs, the organisms that don't use sunlight for energy, they were sort of there, but they were more, the biomass, they were more well developed where there was a lot of hydrothermal activity. Anyway, hydrothermal activity, one automatically thinks of hot smokers, deep sea vents. These are typical for mid-ocean ridges today, but there are also off-ridge events that are lower temperature, the white smokers. Temperatures in the black smokers typically reach up to 350 degrees. In the white smokers, they're a lot less. I think they can be 50 to 150 degrees. They're a lot weaker. But there are also hydrothermal vents in subaerial hydrothermal vents in shallow regions. Now I've got a number of images to show. These are images from hot springs in New Zealand. And what I want you to notice here are this hydrothermal water bubbling up through the sediments, just bubbling up through the sediments, because that's what we will see. It's gentle, it's not violent, but it's just bubbling up through the sediments. Some more images of this. And we will see traces of this kind of phenomenon in the rocks that are 3.5 billion years old. So the more violent traces, of course, are you can see vertical veining here. The white stripes represent silica that's precipitated from hydrothermal fluids. It's white because the grain size of the quartz crystals is quite large. The whole rock, this rock is more than 99% silica, but it's black because it's very, very, very fine-grained. The grain size is about 5 to 10 microns. And not only do we have vertical infiltrations of, obviously, in order to infiltrate a rock like this, to break it apart, it has to be lithified. So we're looking in this case at sediments that were already silicified and lithified. Here there's lateral infiltration. It's following the lamination of the sediment. So maybe the sediment was slightly less lithified to permit this parallel infiltration rather than just completely breaking it apart. So on the outcrop scale, this is a penknife for scale, we can see this phenomenon, and this phenomenon is frequent, very frequent. Now we can see it also at the microscopic scale. So if we look at fine-grained sediments, the scale bar here is 1 centimeter. If we look at fine-grained sediments like mud, not sandy sediments, not porous sediments, but sort of gooey sediments. Think of the Bay of Mont Saint-Michel with that really thick mud. I took out a photograph that I should have maybe left in, because when I was doing this study in the Bay of Mont Saint-Michel, I was wearing Wellingtons, but the mud is so gluey that I turned around and I fell out of my Wellingtons and into the mud. But it's very, very gluey. It's very gluey. It's very, I don't know how to call it, sort of like plasticine. Anyway, in this kind of sediment, volcanic sediment, we can even see tiny hydrothermal veins coming up. This, I mean, this is 1 centimetre. We can see them on a centimetre scale, just gently forcing its way through sediment that's thick sediment, maybe starting to be lithified, and just coming up to the surface here. This must have been a sediment surface. This is a beautiful example. And then another example of the, to give you an idea of the importance of the infiltration of hydrothermal fluids in the sediment. It's really penetrating everywhere. This is our unit, unit 2 of parallel laminated sediments that, as I mentioned, we think are just layers of phototrophic mats that have been infiltrated by hydrothermal fluids. If you look at this, this is a thin section of this particular rock. You can see the finely laminated texture to the rock, and here the laminae have been pulled apart. If you look more closely, you can see the individual laminae here, and this pull apart, in order to pull something apart like that, it had to be plastic, it had to be sticky. It's not broken. The laminae are not broken, they're just pulled apart. So something is forcing them. There's been some force to pull the layers of these mats apart. So this is another indication of the importance of the hydrothermal fluids, the effects of the hydrothermal fluids. And then in an upper area of this mat, you can see these sort of lens shapes. Now the white lenses are quartz filled, it's pure quartz. So microbial mats are very sticky things. It's difficult to cross them vertically, but it's easier to penetrate them parallel to the layers. So the layers, if there's a fluid forcing its way through, the layers bend. You get a kind of lens, a vug shape. And this is an indication that there was something forcing its way through these sediments. So this tells us these hydrothermal fluids were there, or they were there, and they were had an effect. We can also see this if we look at take a cross section of one of these layers. We can also geochemically trace the passage of these hydrothermal fluids. This is a cross section, or the silica will tell you. This is a cross section across one of these vugs, and if you look at the edges are enriched in elements which are typically transported by the hydrothermal fluids: iron, manganese, copper, nickel, zinc, molybdenum, arsenic. They're all lining this vug. So this also tells us, is another indication of the importance of the hydrothermal environment. And finally, I won't bore you too much about this. Other indications, geochemical indications of the presence of hydrothermal fluids in the whole of the area. If we do bulk measurements, geochemical measurements of the rock, we take the rock, we grind it up, we analyze the elements that are in the rock. We find a peak of europium and a slight peak of yttrium, which are typical signatures of fluids coming from hydrothermal environments. Again, this is proton-induced X-ray emission spectrum. In fact, the previous diagram came from PIXI analyses. And the range, the types of elements that we're picking up also indicate that there's been some hydrothermal influence. Now, there's the geochemical data can also give us some really fascinating information about the mix between I'm talking always about hydrothermal fluids coming in, yes, but there was still seawater there, and we can see that. If we have a look at the distribution of, if we look at the plot of European and cesium anomalies, we can see this interplay between seawater influence and hydrothermal influence. For instance, for the europium, value of more than 1 indicates a hydrothermal signature, and this is almost all the samples we measured are more than 1. Whereas with the cesium, the strong marine signal is where it's less than 1, and this is less than 1. So we have we're looking here at an interplay between seawater influence and hydrothermal influence, which is logical. But it's just nice to see this documented. Just briefly to finish up with the hydrothermal story, we can also see influence of the hydrothermal fluids were not always gentle in their infiltration. Here, in this particular horizon, some of the layers have been mixed up by the hydrothermal influence, and it's particularly nicely shown in this Raman spectral map of this particular thin section, where carbon, the black layers are actually carbon rich, and you can see this in the green here. The silica, which is everywhere, is sort of orange, and anatase is an alteration product of the volcanic particles, as in blue, but it's mostly the silica and the carbon which shows you this disruption of the layers. So ad nauseum, you've got the idea. There was a hydrothermal influence everywhere, okay? We can move on now. I've spoken mostly about the areas that were influenced underwater, but there's been some recent studies showing that there are perhaps traces of life in volcanic rocks that were sediments, beach sediments that were exposed, perhaps slightly cracked, and exposed to the atmosphere and infiltrated by microorganisms. I'll speak about these later. This crack, this rock, you can see the sort of cross bedding typical of ripples. We're looking at beach sediments here. These are sands, more coarse grained than the ones that I've been showing you. And there's a small crack here which was apparently open to the atmosphere. And I'll show you some data from this publication. So, the habitats of life. There were habitats, underwater habitats, water at all depths, underwater, shallow water, the beach, intertidal. There appears to be also vadose areas open to the atmosphere. Were there areas on land? We're not too sure whether we have preserved areas that represent land areas at all. Most of them seem to be coastal areas, but there's some debate about that now. And certainly hydrothermal vents and springs everywhere, underwater, on the beach, on land. So I want to talk a little bit now about the characteristics of microbes. I'm going to show you images of fossil microbes, but how can they be preserved? What are the characteristics? Microbiologists of you can now go to sleep for a few minutes, and the rest of you pay attention, please. So, one of the most obvious characteristic of a microbe is its morphology, its morphological characteristics. So, the morphological characteristics refer to the shape, the size, evidence of living processes like cell division, that's that's sort of the life process, and death, where a microbial cell, when it dies, it produces, there's an automatic production of an enzyme which breaks down the outer cell wall, and the internal contents escape. So it's like a balloon that's been blown up and deflated. So you end up like with a sort of sac-like structure which has a rugged surface, perhaps similar to this individual here. And another evidence is perhaps flexibility if we're looking at sort of longish organisms. But the image here is of modern organisms. They're actually they're on a diatom shell. They're degrading the organic sheath of a diatom frustule. And you can see quite a variety in this one image. You can see rod-shaped organisms here. This particular individual doesn't look too happy and is probably dying or dead because it's quite rugged. And normally the cells, when they are living, they have quite a turgid surface. Not all of them. Some cells naturally have a very rugged surface, but most of them have a turgid surface. We have coccoid shapes here, oval shapes, chains of coccoids here, spiral organisms there. So quite a variety of shapes and sizes. The scale bar here is 1 micron. This is another image of the variety of shapes of microorganisms, some of the variety of shapes of microorganisms. These are all prokaryotes. And then, yet again, some really weird and wonderful beasties. Anyway, so there are, although microorganisms generally have very simple shapes, there can be some, at least modern organisms, with quite complicated shapes. Another characteristic of microorganisms is that they are, I'll use the anthropomorphological term friendly, social organisms. They don't like being alone. You hardly ever find a microorganism, a single cell on its own. It's always in a colony with others. So here we have an image of a colony of rod-shaped microorganisms. You notice that they're associated with a thick sort of sheath, filmy-like coating. This is what we call extracellular polymeric substances, and microorganisms produce this material. They live in it. It's in a way it's like their house, because they can control within a thick sheath of what we call EPS. They can control the conditions, the environmental conditions, pH, solute concentration, and so on. And but this particular colony, you only see one particular species of organisms, but they can also form colonies with other species. Each species has its role in the management of the community. They don't all eat the same thing, etc. So generally, colonies tend to be multi-species. I mentioned the EPS, the sheath, the polymer that the organisms produce. Sometimes the polymer can be extremely fine, delicate, as this kind of web-like polymer between. These are, in fact, this is a sample I took from many years ago here in France from the Bay of Bourgneuf. And you can see it's a lovely one of a microorganism in the middle. It's like a spider. The filaments attach it to the mineral surfaces. So, but this is a version, a sort of very delicate type of film. But films can also be extremely robust, very thick. For instance, phototrophic mats that form on beaches are very thick. They have the capacity they can dry out. I picked this one up from the beach in Shark Bay in Australia. It's a phototrophic mat. It's dried out, but if you put it in water, it will come back to life again, because the polymers they're very water rich. They retain the water. They can protect the organisms. So these are robust features. And another example of the morphology, of course, are huge structures that can be produced by microorganisms. I have here some photographs of the stromatolites from Shark Bay. They can form either tabular flat sheets or these beautiful domal structures. These stromatolites are about a meter in high, but it takes something like 7,000 years for them to get to that height. And let me tell you, that's fast. That's fast because these are formed by phototrophic organisms that are oxygenic. when you'll see some stromatolites from the early Earth, these were formed by phototrophs that didn't produce oxygen. They were anoxygenic. So they are they are less, they grow much more slowly. Anyway, so, okay, apart from the actual morphology, the various morphological aspects of the organisms, these organisms are formed of organic molecules. The composition. They can be characterized by the composition of the molecules, the organic molecules. They can be characterized by the elemental composition of the molecules, because the molecules contain various elements, especially transition metals. Some molecules need transition metals to in the structure of the molecule to make it more robust, etc. But the typical molecules that we think of for an organism, DNA, RNA, lipids, proteins, etc., they degrade very, very, very rapidly. And what we end up in rocks after degradation, if we're lucky, if the organic matter is preserved, and the organisms need to be preserved in an anaerobic environment in order for the organic matter to be preserved. Otherwise, they are oxidized. So, what we will look at are the degradation products of molecules that we can relate back to a living organism or an important organism. For instance, hopane can be related back to hoponoids, and phytane is typical degradation molecule of phototrophs. However, sometimes the molecules can become very, very degraded, and they lose their functional group. So you can't relate them back to a precursor molecule of a living organism. And this is especially important over long periods of geological time, and I'm talking about 2-3 billion years time. For instance, this molecule, thiophene, it's a sulfur-containing aromatic molecule. We can find this molecule in organic matter that's 3.5 billion years old, and I'll show you the documentation of that. However, this molecule is also found in carbon in meteorites. So if you only had this molecule to go on, you couldn't say whether it came from organic matter that came from life or from abiotic organic matter. So, and again, the elemental composition is important, because organic matter is, organisms are not made just of carbon, or all the other elements, especially hydrogen, nitrogen, oxygen, phosphorus and sulfur, as well as the transition metals. Now, there's also the fact, another characteristic of organisms is that they prefer to use the lighter isotopes of elements if they're available. For instance, with carbon, organisms fractionate carbon, and in fact, the typical you can find the carbon signature of organisms tends to be in this. It can go from just above minus. Well, it's C13 over C12. The organisms prefer the C12. So we measure this as delta C13 per mil. Carbonate, inorganic carbon, is around 0, but for organic matter it goes up to minus 50 per mil and even more. Keep in mind, though, that the carbon fractionation of abiotic carbon in meteorites covers the whole of this range and goes much further towards the positive as well. It's got a broader, it overlaps with the microbial fractionation pattern, but it's got a broader range than the microbial fractionation pattern. Metabolism. Another characteristic of organisms is that they metabolize. Now, these are processes. How can processes be preserved in the rock record? They can only be preserved if the processes have an effect on the immediate environment. So, Microbes like surfaces. Most microbes are surface related. And here are some images of microbes on the surfaces of minerals such as quartz or feldspar. Now, certain microorganisms, chemolithotrophic microorganisms, they obtain their energy from oxidation reduction processes occurring at the surfaces of the minerals. And they can also obtain transition elements by enzymes that are exuded and that dissolve away the mineral surface and release the elements that they like. If you think about the early Earth, Hervé will have told you about the volcanic materials, the ultramafic and the mafic volcanic materials are rich in elements that the organisms love. Iron, magnesium, cobalt, all the transition metals, they're all there. So chemolithotrophic organisms love to, let's say, eat. These are the rock eaters. You can see the effects of the presence of microbes on minerals. For instance, we have here, this is from work by Jill Banfield a while ago. She did an experiment to expose, I think this is calcite, to expose calcite to fluids with or without organisms. Above, you can see the corrosion of the calcite where there are no organisms in it. And below, you can see the corrosion with organisms and organic acids and so on. And you can see some traces of the organisms. And the physical structure is different. There's a difference between the two. And this is due to the presence of the microorganisms. The presence of microorganisms can also influence the precipitation, the structural characteristics of minerals. For instance, here we have a crystal that's perfectly precipitated in a fluid that contains no organic matter. Same crystal precipitated where there are organics. It has defects, and that's because the organics they chelate to the mineral surfaces, and they prevent perfect precipitation. And this is perhaps the most interesting and the most significant one. There is a hole in this particular mineral. I've forgotten what it was, but you can see that there's filmy material inside. This hole was created by the presence of a microbe sitting on the mineral, and it dissolved it to get the nutrients. So, and the final aspect of microbial metabolism is the fact that minerals can be precipitated as a result of microbial metabolism. Yesterday, Hervé, when he was talking about the Allen Hills meteorite, you spoke about magnetotactic bacteria and chains of magnetosomes. These are deliberately precipitated by the organisms, but they can also be mineral precipitation can also be a byproduct of organisms. For instance, part of the growth of stromatolites, mostly it's due to because the photosynthetic mats are sticky, so sand grains can stick on them. But you can also get precipitation of calcite within them. It's not the phototrophic organisms that precipitate the calcite, but the phototrophic organisms in the layer. It's the upper layer that is living. In the lower layer of the photosynthetic mat is dead, and it's being degraded by heterotrophic organisms, chemotrophs, such as sulfate-reducing bacteria. And it's the activity of the sulfate-reducing bacteria that can lead to the precipitation of calcite. And this is why stromatolites can be calcified. So this is another, and these are all, whereas we can't, processes cannot be locked in the rock record, but the results of the processes can. So we can get some information on that. So before the break, I'm just going to finish off with some information about how microorganisms preserve. I've shown you the various characteristics, morphology, organic composition, results of their metabolic processes. But let's go on now to how they preserve. Think, we don't have dinosaurs, we don't have shells, nothing juicy like that, but just lumps of goo, lumps of organic matter. But they can be preserved. I think I couldn't put, there are a couple of slides I wanted to add to the presentation, but I couldn't because my computer's playing up. But I want you to keep in mind that when I talk to you about the actual physical preservation of the microorganisms, the fossilization of the microorganisms, what we see in the rock record is only a portion of what was there. We don't see everything because a lot of things, most things, do not preserve that way. Most microorganisms just degrade and their organic matter just goes bleh and sort of dispersed in the sediments. Most of them don't fossilize. So what can be preserved? I've spoken, we can preserve degraded organic molecules. These will be preserved in anaerobic sediments. We can find them in lithified sediments. Sometimes they can be found also associated with rock surfaces, for instance, pillow lavas. And the kinds of signatures we can find are the carbon molecules themselves, isotopic signature, etc. Now, if the organisms are quite robust, this is not the case for the very early organisms, but later organisms, things like spores, for instance, they've got quite robust membranes. They have to, because they're supposed to preserve the genetic material for however long is necessary for the organism to come back to life. So these organisms have very thick membranes, and they can be deposited with fine-grained sediments, anaerobic sediments, and they're flattened. So you can see the flattened remains of these cells. So you have a physical signature, the flattened cell, or organic cell. You can measure the carbon molecules again and the isotopes. And then there are the organisms that are actually replaced by minerals. The replacement can be exquisite, and I'll show you some really beautiful, beautiful examples. I have to say I'm very subjective because I like this subject. This is my own personal subject, so take me with a pinch of salt. This can happen in any kind of sediments and rock. It can be anaerobic or aerobic. So you can have the fossilized cells, colonies, even structures like stromatolites, carbon molecule, and if in the anaerobic environments, if the carbon's preserved, you can analyze the carbon molecules and the isotopes. Okay, another one of my sketches. Imagine we're looking at sediments. These are volcanic particles, and the sort of red stripes are colonies of microbes on the volcanic particles. There's no particular preservation here. The organisms, the colonies die. Their organic matter just becomes a generic organic matter that's indicated by the sort of red stippled area in these sediments that are then lithified. Then, in this case, the organic matter is dispersed in the sediments. And we end up with, if we're lucky, we end up with biomarkers that we can relate back to a specific molecule related to a microbe. Or if it's really old and degraded, an organic molecule, but we can't really relate it to anything particular. Then we get the squashed organisms. These are just, as I mentioned, organisms with a robust membrane that happen to be sedimented, deposited with sediments, and they just get squashed with the sediment, and you end up with a flattened cell. This is an example from Emmanuel Javot, who's spoken here before. Beautiful example of what we call an acritarch. These are the spores. The size here is about 10 microns, and you can just see sort of nicely flattened organic shell. Then we have the preservation, the mineralization, permineralization, fossilization, whatever you want to call it, the mineral replacement of organic cells. And these can be preserved in sediments, anoxic or oxic sediments. So we have these three major means of preservation. One is missing that I realized yesterday I didn't put in, and that is there are organisms when they're on the surfaces. I showed you that they can corrode the surfaces of a mineral, and they can leave a hole, a mold, and the molds can be preserved. I'll show you some examples of that. So you have these main means of preserving the organic signatures. The question now is, okay, we know that there are different ways of preserving a signature, organic, metabolic, or physical, of a microorganism. How do we identify it in the rock record, especially when we're looking at the oldest preserved sediments in the world? So, and there are a lot of pitfalls. Okay, analysis of the presumed biosignatures. Okay, first of all, we need to document what they are. If there's organic matter there, analyze the organic matter. See if there is a biomarker molecule that can be related back to a living molecule. Analyze the geochemical signatures, like the isotopic signature or any kind of elemental concentrations and so on. Once we've decided, once we've done this, then we have to really make sure that these traces, do they represent a living object, or is it just an artifact? And I'll show you some examples of the artifacts. So one of the most important things is the feature we're looking at, is it related to originally to a living organism, or is it something completely different? Once we've decided that, yes, it is related to a living organism, we have to decide, okay, but did it form at the same time as the rock? Because rocks have fractures. Many of these rocks contain carbon. Many of these rocks contain transition elements that are interesting for infiltrating organisms, endolithic organisms that like to infiltrate cracks, take the nutrients from the cracks. So, and sometimes these organisms can also be fossilized even. Anyway, so it's the question is, we have a rock here. This is actually from the Gunflint Formation in Schreiber Beach in Ontario on the north coast of Lake Superior. It's 1.9 billion years old, and this rock contains many structures. You can see some sort of filamentous structures, some round-shaped structures. These are actually the remains of microorganisms. But how do we get from that to this? In fact, well, first of all, most important, of course, is observing the general geological environment, get an idea of the environment that we're looking at. And we see these sort of typically oval stromatolitic structures here. These are very big features, so you don't see the domes quite so easily here. And then we take a thin section, as I mentioned, 30 microns thick from this rock, and you can see this sort of columnar like features. The brown is actually organic matter. And looking in one of these layers, we can detect structures that here it looks like a chain of beads, thinner one, thicker one here, some rounded structures. Now, these organisms are, in fact, microfossils from this particular formation were the very first ancient microfossils to be identified. They were identified by Barghorn and Tyler, I think, in the 1950s, who studied. Well, they were just studying the rocks, and they suddenly saw these features, and they thought, "That's funny. They look at rather microbial," and did further studies. And indeed, there's quite a variety of microbial structures preserved in this rock. They are actually silicified. So these ones we can actually see in the thin section. We can see that they're in the rock. We can see that they are related to particular layers that can only have been formed at the time that the rock formed. So we can be fairly sure that these features formed in situ. They were there at the time the rock formed. More difficult, for instance, are features like these that are very small. In fact, let me just go back. These are big. Look at them, 100 microns here. So these are big beasties. Now, go to much smaller ones. This is a more difficult example. This is a rock from the Pilbara in Australia. It's about 3.5 billion years old. I'll talk in more detail about this, but I just want to speak about the preparation, the means of observation here. In this rock, we see features such as these, what look like dividing microorganisms. We can only see them with the scanning electron microscope. But how do we get from that to this? I will show you. First of all, going back to how microbes fossilize. If you imagine your microbial external wall, it's full of functional groups. It's like imagine a hedgehog with all these functional groups standing up. Well, in a fluid that's saturated with minerals in solution, for instance, silica or calcium carbonate or whatever, these minerals precipitate onto these functional groups. It's a purely chemical process. It's biomediated, but it's not biocontrolled. It's a purely chemical process. The minerals fix themselves onto functional groups such as carboxyls, hydroxyls, phosphorylls. Also, they can use cation bridging. For instance, if there's iron in solution and the iron fixes to the functional group, it's maybe easy for a molecule to precipitate onto that functional group. Now, this is the only point where the organisms are involved, in the sense that the precipitation occurs because the organic matter is there. The rest of the process is purely chemical. For instance, let me go back. The rest of the process, once the minerals have fixed onto the functional groups, more minerals precipitate on them. It's polymerization. It's simple polymerization. So we've got, as I mentioned, I do experiments with fossilizing microorganisms. And what you see here are some thin sections of microorganisms. The scale bar is 0.1 micron, 100 nanometers. Okay? So we take, with a microtome, we take slices of microorganisms that are in the process of being fossilized. These ones were put into silica. And here you can see some black spots around the edge of the This is the outer wall of the microorganism. You can see some dark spots. This is where the minerals are starting to precipitate on the surface of the microorganism. Leave it in the fossilizing solution for a while, and you get polymerization. You get a crust forming. And the dark matter inside is the poor organism. It's died, of course, so its organic matter is starting to degrade, and it's mixed in. It's also mixed in with the mineral, the precipitating mineral, and it's trapped in the inside. Now, imagine in this image that the red spots are your fossilized microorganisms, and the grey is the precipitating mineral matrix. These organisms are trapped in a mineral matrix. So this is your rock. You fracture it. You have a fractured surface. You can't see your minerals because all you see is, you can't see the fossilized microorganisms. All you see is the mineral surface. And whereas, if you're looking at fossils, big fossils like dinosaur bones or shells or frogs or whatever in a rock, you can go in with a hammer or a chisel and very delicately chisel away the rock around it. You can't do that here. So we do that, but using a chemical process. We use an acid. We etch the surrounding mineral with acid. And what happens is that the acid will attack the pure mineral, and it will leave the dirty mineral, i.e. the fossilized microorganism, exposed. Wait for it. Ta-da. There you are. This is what happens in nature. This is a quartz crystal. And I've taken this actually from a rock from South Africa, 3.44 billion years old, rock reef for Hervé, so that he knows where it comes from. You can see the etching features on the quartz crystal, but in the middle there's something that's half coming out. It's still half embedded in the mineral. And you can see features that indicate that it's possibly a fossilized microorganism. It has, oh, thank you very much, Hervé. You can see that it's still half embedded in the quartz. It has a sort of rugged surface. It's got a shape and a size. I forgot the size. In fact, this is about 1.5 microns in length. It has a shape and size that's similar to microorganisms, sort of rugged surface, and there's a bit of goo that has an organic look attached to it. And it also contains carbon. So this is a very good example of how to expose fossilized microorganisms in these ancient rocks. And I can tell you, this is one of the very best examples I've ever seen. I've been doing this work for 20 odd years. It's very difficult. Most of the time you etch too much, so you lose it, or you etch too little, so you don't see it. And just sometimes you get the right time and whatever, and it works. And this is one beautiful example. However, there are a number of problems, and I'll just quickly finish with the problems before you go for coffee, or is that okay? Just 5 minutes? The problems are that there are some mineral and organic structures that can look like fossilized microorganisms, but aren't. They physically resemble these fossilized microorganisms. And then, as I mentioned, in terms, especially with respect to the carbon isotopes, organic carbon, when it's very, very old, well, it can have the same isotopic composition as abiotic carbon. And when it's highly degraded, it's so degraded you cannot relate the molecules back to a particular component of a living organism. So this is the question of biogenicity. Is what you're looking at biogenic? Is it the rest, a trace of an organism? Or, and the final thing is, did it form at the same time as an organism? So we'll have a quick look at the problem of biogenicity, abiotic versus biological. Now, in the upper images, I'm showing you here what I have interpreted as polymer produced by organisms. You can see a sort of globular kind of texture to the polymer. And you'll see this in more detail in later images as well. A globular kind of texture here, and a sort of filmy kind of texture between the quartz grains here. And this is from rocks that contain traces of fossilized microorganisms. This is actually from Australia, almost 3.5 billion years old. However, I did an experiment using an extract of a carbonaceous meteorite, the Murchison, which I deposited on volcanic minerals as we find in the early Earth. And I just saw sort of a globular kind of holy structure, which frankly I would not be able to distinguish these two. And again, or a thin film between mineral grains. There is no way, just seeing these images, I would be able to say, is this biological or not? Impossible. Also, microorganisms, although I've shown you microorganisms with weird and wonderful shapes, they tend to have simple shapes. Take the coccoids, for instance. They have simple round shapes. You can see them, some in cell division here. However, certain minerals like silica, which is a problem because silica is the mineral I use, hydrothermal silica can also form spheres that look almost as if they're in cell division. Tricky. What about syngenicity? The best way to determine whether the features you're looking at are really in situ, whether that you need to determine that they were formed at the same time as the rock. First of all, check your rock for porosity and fractures. Make sure that the area you're looking at is not a fracture area, sort of a natural fracture area, not just a fracture that you've created with your hammer. Note that infiltrating younger organisms can also be fossilized. Again, I can't show the image because my computer's going haywire now. So basically, what you have to determine is that if you're looking at a fossilized structure, make sure that you have to be able to determine that it formed before the lithification of the sediments, before the lithification. And if possible, and this is difficult, use multiple samples. So just quickly some images. In this particular image, we have from the Pilbara a rock that's 3.44 billion years old. You can see it's an image of a thin section in backscatter, and you can see the quartz crystals. The sediments, when the sediments silicify, as I said, they're infiltrated by silica-rich fluids, which polymerize and then slowly lithify. And then, because we're talking about rocks that are about 3.5 billion years old, they are subjected to metamorphic processes, heat and a little bit of pressure. And the silica recrystallizes. It forms small crystal sizes. These are so these are the angles that you can see of the recrystallized quartz crystals. Now you can see certain filamentous structures that are jumping in and out of the quartz crystals. These features, which have a very sort of flexible, non-mineralogical type of structure. Anyway, they were there before the quartz formed because they cross the boundaries of the quartz crystals. All we can say here is that these features formed before the metamorphism of the rock, but had to be there also when the rock was first silicified. So they were there before. And again, here, there's no doubt about it. This structure is still half embedded in the quartz. It was there before the quartz was formed. So this is the kind of thing that we're looking at. I think I'm going to stop here for a break. Okay? Thank you.